Hello, class. This is Mr. Hart. And in this podcast, we want to start our end of year topic on special relativity. Okay? And you've probably heard some weird things about special relativity with maybe time slowing down and things getting shorter, but we want to go into mathematically what's happening, physically why it has to happen, and so on. So before we get too far into it, let's just talk about what special relativity means and why it's called that and where the phrase comes from. Okay? So special relativity is just the study of anything or any frame that is going at a constant velocity. So relativity in general is just the study of reference frames. Okay, so special relativity is the study of constant velocity reference frames. Okay, that's what it's called. Special. It just means they're going at a constant speed. Okay, that's not very common for frames, reference frames. Okay, but we're looking at this case where they're going at a constant speed. General relativity, which you may have heard of as well, is the study of any frame, whether it's accelerating or just going at constant speed or anything like that. So that's why it's called special relativity, because they must be going at a constant speed. Okay? And again, special relativity is known for kind of some of the strange results that come from it, and it's because we know these two facts. Okay? We know that in any reference frame, okay, the velocity of the objects that you observe is dependent on the frames that it's observing from. So for example, you're driving down the highway, right? You're going 60 miles per hour. You see a car pass you at 60 miles per hour as well. Okay? To you, that car looks like it's zooming at 120 miles per hour because your reference frame is also moving, right? So 60 plus 60 makes it look like it's going 120. Or if you're both heading the same direction, right, then you look like you're not moving relative to each other, right? We've done this in basic physics, right? At the beginning of the year, we talked about reference frames. Okay, we know that. Okay, but we also know that the speed of light is constant in all frames. So if you're driving in that car and then you turn on the headlights are still going at the speed of light, regardless whether you're moving or not. Okay, so this kind of leads to a problem because these seem to contradict each other. Okay, the speed of light should be changing depending on what frame it's being observed from, but it doesn't. Okay, so one of the first people to kind of analyze this is Albert Einstein and a lesser known man by the name of Lorentz. So both of these men were kind of known for looking at these paradoxical statements and trying to find a way to resolve them, find an answer to this paradox that's being created. Okay, and one of the examples they use is a thought experiment called the light clock. Okay, now I have a link to this video, but you should have watched this video by Doc Physics. He does a great job of explaining the light clock experiment and kind of deriving the equation that comes from that. Okay, but just to kind of summarize really quickly, the experiment was if you have a person on a train and they have a light clock or light that's just bouncing back and forth on this mirror, okay, compared to someone that observes the train from the outside, they would see the light go down and back up and down and back up and so on, right? So in these two reference frames, the light appears to be traveling a longer distance on this frame compared to that frame. And because of this result, the only way to summarize this mathematically and give a solution that's consistent is that the time has to be different in both of these reference frames. Okay? And so when all is said and done, when you've watched that video, you end up with what is known as the Lorentz Factor. Okay? And the Lorentz Factor is basically just a ratio of how much faster time appears to be moving to someone compared to someone else in a different reference frame. Okay, so this is gamma. This is what we call, I guess I'll just point to this. This is what we call the Lorentz Factor, and it's that ratio of time difference between two frames. Okay, and you can see it's dependent on the velocity or the relative velocity of the frame, okay, over the speed of light. Okay. And so when we put this in the calculator, we'll see some interesting things that come from it. But basically, it's just a factor named after Lorentz that tells you how much faster time is flowing for someone. Okay? And this is kind of crazy to think about, that time actually changes speed depending on who is observing it. Okay? And so we'll look at some problems that give some interesting solutions, but just kind of wrap your head around this. Time can flow faster or slower depending on how fast you're moving. Okay? All right, so let's look at if we actually plot the Lorentz factor. Okay? So in this case, it's a function. But this is the value of the Lorentz factor. Okay, so this is gamma on the top. And then this is velocity compared to the speed of light. Okay, so 1 would be the speed of light. Okay, now if you analyze this function, okay, notice that for small speeds, it's almost exactly 1. Okay, basically, we can't see a whole lot of difference in the Lorentz factor for very small speeds like we're used to. Okay, that's why when you're running by a friend, you don't seem to be flowing through time slower than they are. Okay, we don't see it at the very small speeds. You really don't start to notice it until about 0.5 c, okay, or about half the speed of light. Okay, so you have to be going about half the speed of light before you really start to notice anything changing as far as time. Okay, and then obviously the closer and closer you get to the speed of light, you'll notice that it picks up very quickly. Once you get to about 0.8 c, okay, it picks up quite a bit, and then you can really start to see time slowing down. Okay, and so again, this is why we don't usually notice this effect at the speeds we're used to, because it's so small that time pretty much is the exact same for everyone. Okay, that doesn't mean we haven't been able to detect this. There's actually been atomic clocks that we've put on like airplanes that are going, 500 miles per hour or somewhere around there. And after a while, they will see the clock slow down enough that they can detect it. Again, it's maybe a couple microseconds, but it is something that we can measure, and we have seen this effect occur at smaller speeds. Okay, but for most of the problems we do with special relativity, we're going to have to be going pretty fast before we notice anything mathematically. Okay? All right, so here is our final equation. Okay, this is the time dilation equation, basically describing how much faster or slower time is moving. Okay, so the equation basically reads this way. T equals T naught times gamma, or the Lorentz function, or Lorentz factor, I mean. Okay, but this is the time according to an observer. Okay, someone watching something else moving. This is the time relative to someone that thinks they're sitting still, or from their reference frame. I don't know how to say that, but time of reference frame. They're going to think they're sitting still, okay, and time's just flowing normally. Okay, and then last of all, you times that by the Lorentz factor. Okay, all right, so keep in mind the Lorentz factor is always greater than 1, okay, which means this number times Lorentz factor is always going to give a bigger number. So the time that the observer sees is usually going to be faster or longer, I guess you can say, than the time of the person that thinks they're sitting still. Okay, and again, it's kind of tricky to know which one's which, but just remember the gamma factor is always going to be bigger, okay, than 1, so you should end up with a larger number in that case. Okay, all right, let's try some example problems, and then I think we'll be able to kind of sort this out. All right, so we have an astronaut in his spaceship travels at 0.6 c, or 0.6 times the speed of light, for an hour according to his clock. How much time has passed on an Earth clock during the space flight? Okay, so what we got to do is we say, okay, we know that in this case, we know the velocity is 0.6 c. Okay, and we know that the time of the astronaut, okay, who thinks he's sitting still according to his reference frame, okay, according to his clock, is 1 hour. So that's going to be T naught. Okay, so what we need to do is we set up that equation. Okay, and before we do that, let's just calculate the Lorentz factor. Okay, we know that we're going to be plugging into T equals T naught times Lorentz factor, but let's actually calculate the Lorentz factor first. Okay, so Lorentz factor is 1 over the square root of 1 minus v squared over c squared. Okay, so what we're going to do is we're going to replace v squared with this 0.6c. So we're going to get 0.6 squared and c squared. Okay, and what you'll notice in most of these problems, the c squared is going to cancel out. okay, which is nice. We don't have to worry about it. So basically the Lorentz factor is 1 over 1 minus 0.6 squared. Okay? So then we can just plug that into our calculator and we'll get the Lorentz factor. So 1 divided by the square root of 1 minus 0.6 squared gives us that the Lorentz factor is 1.25. Okay? So what does that mean? It means that time is flowing 1.25 times faster on Earth compared to the astronaut. Okay? So there we go. We know that gamma is 1.25. Okay? And it's just a ratio, so there's no units. Okay? I'm going to clear this side so we can do more of our calculation. And just remember that gamma, well, the Lorentz factor is 1.25. Okay? Now we can plug it into here. So t, according to Earth, the time on the observer's reference frame is equal to his reference frame, which was 1 hour, times the gamma function or gamma factor, which is 1.25, or basically it's going to be 1.25 hours. Okay? And there we go. So that's how much time will have passed by on the Earth clock. Now we could put that into minutes or seconds, whatever the problem needs, but in this case we can just leave it in hours. Okay? But there we go. So we have figured out how much faster time is passing on Earth compared to the astronaut. All right, let's go ahead and try another one. So in this problem, tired of dealing with aging creams and other ointments, my grandpa decides that he is actually going to age half as fast by using special relativity. He actually said this to me once. He wants 1 year to go by for him while 2 years go by for everyone else. How fast would he have to travel to accomplish this? Okay. So in this case, we're not given a whole lot of information. We just know that time passes twice as slow for him or twice as fast for everyone else. Okay. So in other words, what we have to do is we have to figure out what gamma is just based off this information. Okay. Well, in this case, we know that 1 year equals 2 years, right? So in other words, the Lorentz factor has to equal 2. Another way we could have written that is that we could do 2 over 1, right? 2 years goes by for everyone else for every 1 year that goes by for him, okay? But either way, the Lorentz factor is 2, okay? So then if we're trying to figure out how fast he's going to have to travel, we just have to solve for the Lorentz factor equals 2, okay? So we know the Lorentz factor equals 1 over square root of 1 minus v squared over c squared. All right, I just rewrote this over here just to give me a little bit more space. But our goal is we need to figure out what v is, so we need to solve for v before we can plug anything in. Okay, so the first thing we're going to do is we're going to square both sides. So we're going to get gamma squared equals 1 over 1 minus v squared over c squared. Now we're going to make this stuff on bottom switch places with gamma. So we're going to times everything on the bottom over and divide by gamma. So that will give us 1 minus v squared over c squared equals 1 over gamma squared. Okay. Then, after that, we will add v squared over c squared to this side and minus this over to the other side. So we get 1 minus 1 over gamma squared equals v squared over c squared. Okay, and then the last step is we square root both sides, and that cancels out the v squared and the c squared. So we end up with v over c. Okay. So when all is said and done, we end up with this derivation right here. Okay. And notice that I leave the c on this side. That means I'm going to be able to express my answer in terms of c. Okay. So now I can start plugging in this value we just figured out, the gamma value, and figure out how fast they're going to have to be traveling. Okay, so we're going to get square root of 1 minus 1 over 2 squared, which is 4. Or in other words, that's going to be the square root of 1 minus a fourth, which gives us 3/4. Okay, so we can just plug that into our calculator. Square root of 3 divided by 4. And that gives us 0.866. Okay? Now keep in mind, I left the c on that side, so in reality, this is 0.866 c. Okay? That's my answer. Okay? So they'd have to be going, or my grandpa would have to be going 0.86 c times the speed of light for time to flow twice as slow for him. Okay? And there we go. That's our answer. That's the velocity he'd have to be going. Okay? So hopefully this kind of helps you kind of figure out how to do the math with special relativity. It's kind of a weird thing to think about with time changing speeds, okay? But hopefully this kind of made sense. Let me know if you have any questions, and thank you for watching.